Okay. So far we've talked about many different kinds of linear maps. So there was a linear map from U to V. These were called linear maps. But if you had a linear map from V to V, which was, so these are functions from V to V that satisfies linearity, okay? Yeah. And these are called what? We call these as operators. So linear maps that whose target space and the domain are the same, that's called operators. Now, to talk about Riesz representation theorem, we now have to talk about linear maps from V to its base field F, okay? And these are called functionals. So in functional analysis, often the topic of interest are these functionals, where a lot of the functionals are integral functionals. Like if you have a function, in function spaces are usually infinite dimensional spaces where functions are vectors, right? So if you take a function and map it to integral from 0 to 1 of f of x dx, then it gives you a number, right? And integration is linear, so this is an example of a functional, right? Okay, so if you have a functional, then there's something called Riesz representation theorem. Suppose V is finite dimensional inner product space. Okay. And phi is a linear functional. Okay. Then there exists a unique, so if you put E backwards and put an exclamation mark, that means there's a unique U in vector space, so that phi of V is equal to VU for all V in V. Okay, let's prove this. Proof. Well, because it's finite dimensional, we know that there exists an orthonormal basis, right? We just proved it. So let E1 through En be an orthonormal basis for V. Okay. Then for any V and V, we now have V must equal to A1 E1 plus da 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 AN EN. Okay. Now, because phi is a linear functional, being linear means addition split and any constant can be brought outside, right? So by definition, this is going to be equal to phi of A1, no, A1 times phi of E1 plus da 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 AN times phi of EN. Now let's compare this with some U. So I want these two to be equal, right? So what I'm going to do is I'm going to take this one and plug it on the right side. So I want to do V U, which is A1 E1 plus da 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 AN EN U. But that's going to be equal to A1 times E1U plus da 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 AN times ENU, because we know that because we know that the inner product is linear in the first argument, right? So we have this. Oh, so it looks like we know what to do. It seems like I need E1U to be phi of E1 and ENU to be phi of EN. Okay. So can we make that happen? Well, now what we are going to do is we are going to now write down U as U equal to B1 E1 B and EN. Okay. So that EK U, well, if you do inner product of this with this, because this is mutually orthogonal to every one of these except for EK itself. EK is 1. That's what orthonormal means. So this is only going to give you non-zero for EK when you have BK EK, which is going to be BK bar EK EK. Remember this, it's sesquilinear, so that any constant coefficient on the second part, when you bring it outside, you're going to have a bar on top. So that's going to be BK bar. Okay, and then that is going to be, that will have to be, because I need EK UK to be phi of EK, so E1 U should be phi of E1 and so on and so on. So I need this to be phi of EK. So here I'll put want. I want this to be that. So okay, so that almost gives us what we should do. So therefore, if we define U to be BK should, so that means BK should be defined as phi of EK bar, right? So if we define U as phi of E1 bar E1 until phi of EN bar EN, then we have VU equals to phi of V. Okay. That's going to work out because once you have that, then EKU is going to be equal to phi of EK, and if these are individually phi of EK, then that's equal to that, which is equal to that. Okay. All right, so I have to admit that this is not a good proof. A good proof does this. You work this out, okay? You work this out and you write backwards, okay? So that's why reading proofs are hard, because often the proofs themselves are written in the opposite order of discovery. When you discover something, once you find the discovery, then you write it backwards. So what you do is you start from here. So this much over here, this much is a discovery procedure, which you don't write at all, okay? And then what you do is you don't write this at all, and you write this, and you define U as this, as if you're pulling the rabbit out of the hat. Like the magicians, they pull the rabbit out of the hat, right? Just appears out of nowhere. So if this appears out of nowhere, it's like people are just merely reading the proof will be like, hey, where is this coming from? But there's a reason. There was a discovery process which is not shown to you. And what's being done is VU is now equal to AE1 plus A1, E1, da da da, AN, EN, and then U, which is equal to A1 times E1U, da da da, AN times ENU, and then you say that this is A1, E1, and then phi E1 bar, E1, and then you see that this times this will be 1, but all the other ones will be 0, so the only thing that comes out of it is this comes out as a conjugate, so that's going to be A1 phi E1, right? But then because of the same kind of calculation, this is going to give you the same thing. It will be AN phi of EN. But then by the linearity of phi, this is going to be same as phi of A1 E1 da da da, AN, EN, and that's exactly the same as phi of V. So this equality is now proved. Okay, so that's how it's going to be written. Writing of the reverse order kind of made you confused, but that if you skip this portion that I'm erasing, and you go here to here, then that's a full proof. Okay, yeah, that's a proof. But it's not complete yet because we showed existence, right? We now have to show uniqueness. So let's prove uniqueness. So to prove uniqueness, suppose there was a U1, U2, both gives us phi of V equals to VU1 and VU2. Suppose we had two different vectors that gave you the same representation of V. In that case, we need to show uniqueness, which means U1 has to be the same as U2, right? So what we do is we can now take this one and rewrite it as VU1 minus U2 equal to 0. This implies this because of sesquilinearity. You can move this to the left side, and subtraction can go inside. So this is what you get. But this is true for all. So if this is true for all V, then this is true for all V as well. Now we take the special case where V is instead exactly equal to U1 minus U2. Since this is true for all v, we can choose v to be u1 minus u2, right? So we can specialize to a case when v is same as this, but look, this is vector inner product with this self equal to 0. Now, when you have a positive definite form, when can this happen? Only when
V is 0.
u1 minus u2 is 0, right? So this is true only when u1 minus u2 is 0, so that u1 is equal to u2. So that settles the uniqueness.